Welcome to the Electrical and Electronic Engineering lecture series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is on modulation part 2. We will be completing our modulation of AM spectrum. We will start with power associated with AM spectrum. It has been shown that the carrier component of the modulated wave has the same amplitude as the unmodulated carrier. However, the modulated wave contains the two sideband components as well. It is therefore obvious that the modulated wave contains more power than the carrier had before modulation took place. Also, since the amplitude of the sidebands depends on the modulation index, then the total power in the modulated wave will depend on the modulation index also. Recall that power is proportional to RMS volts squared value. Total power transmitted, that is PT, is equal to the power in the carrier, PC, plus the power in the two sidebands, PSB. Therefore, the total power in the AM wave is given as PT equals AC squared over R plus LSB squared over R plus AUSB squared over R. Equation 9, very important. Where R is in ohms, AC is the RMS value of the carrier voltage, LSB is the RMS value of the lower sideband voltage, and AUSB is the RMS value of the upper sideband voltage. If we put that in equation 9, it gives us that the P in the carrier will be PC equals AC squared over R, which is AC over root 2 squared over R, which is AC squared over 2R, equation 10. Similarly, from equation 9, PLSB is equal to PUSB, which is equal to A squared SB all over R. Expanding further, we give MSC over 2 over root 2 all squared divided by R. Expanding that gives M squared over 4 times AC squared over 2R, equation 11. If we substitute equation 10 and 11 into 9, it will yield PT equals PC plus M squared over 4 times PC plus M squared over 4 times PC. First term is the power associated with the carrier. The second, the power associated with the lower sideband. And the third, the power associated with the upper sideband. Simplifying further, we give the ratio of the total power to the carrier power as in equation 12, which is PT over PC equals 1 plus M squared over 2. Equation 12 shows that the maximum power in the AM spectrum is PT equals 1.5 PC when the modulation index M is equal to 1. This is important because it is the maximum power that an amplifier must be capable of handling without distortion. Note, 1. The maximum power in the sidebands is 50% of the carrier power when M is equal to 1. The use of DSB-AM for broadcast purposes are based on I. It simplifies equipment at the transmitter and receiver, thus reducing cost. II, an envelope detector can be used at the receiver. It is easy to design and does not call for any critical adjustment. 3. SSB, single sideband suppressed carrier, gives considerable savings of power. 4. SSB SC offers great savings in bandwidth since only one sideband is transmitted. 5. Double sideband suppressed carrier system is not very practicable because the modulation of the received signal requires the reinsertion of the carrier at the receiving end. The carrier must be of the correct frequency and phase as the original carrier in order that the received signal may be correctly demodulated, else it cannot be detected by the receiver. Alternatively, a low-power pilot carrier, some 26 dB below its normal value, may be transmitted and is used at the receiver to phase lock a local carrier. AM modulators. The function of an AM modulator is to modulate a carrier wave, which results in sum and difference frequencies together with the carrier. This may be achieved using transistors operating as nonlinear or linear modulators. One example is the Cowan modulator. The Cowan modulator is a typical modulator used in AM transmission and is also known as ring modulators, invented by Frank A. Cowan in 1934. It is referred to as a ring modulator because the analog circuit of diodes originally used to implement this technique took the shape of a ring. See this link for more information on ring modulators. This circuit is similar to a bridge rectifier, except that instead of the diodes facing left or right, they go clockwise or counterclockwise. When A is negative with respect to B, the diodes are reverse biased and appear as an open circuit across the network, thus allowing audio signal to get through. The carrier wave has a square wave switching action on the audio signal. The carrier, which alternates between positive and negative currents at any given time, makes one pair of diodes conduct and reverse biases the other pair. The conducting pair carry the signal from the left transformer secondary to the primary of the transformer at the right. If the left carrier terminal is positive, the top and the bottom diodes conduct. If the terminal is negative, then the side diodes conduct, creating a polarity inversion between the transformers. A particular elegance of the ring modulator is that it is bidirectional. The signal flow can be reversed, allowing the same circuit with the same carrier to be used either as a modulator or demodulator in low-cost transceivers. Effect of noise in AM modulation. In our module 001, it was stated that noise affects the signal more in the channel, that is, during transmission. This noise may take several forms, of which the most common ones are: 1. Extraterrestrial noise, also known as the impulse noise, such as caused by lightning discharge or commutator aching in electrical machinery. 2. Gaussian noise, both natural and artificial. 3. Crosstalk and co-channel interference arising from adjacent broadcast channels that have spectra which overlap the spectrum of the signal being detected. 4. Unfiltered high-power radar harmonics. The above listed noise components are taken care of at the receiver or at the receiving end by: 1. Choice of the antenna. The antenna must be able to discriminate against unwanted frequency. 2. Having parallel working channel, which is also known as the redundant channel or hot standby. By parallel working channel, we are looking at when both the upper sideband and the lower sideband are being transmitted because they are carrying the same information but at different frequencies. 3. Making the front-end electronics at the receiving end to be of high gain. 4. Digitizing the transmitter signal. This helps to introduce redundant bits so that error detection and correction can be carried out at the receiver. 5. Making use of antenna height diversity. And 6. The major way of reducing noise in AM system is by increasing the power of the transmitted signal, and this usually increases cost. Thank you for listening. Please like, share, and subscribe so that subsequent models, more especially part 3, the concluding model of modulation, we get across to you.